Hello again. This video is going to be about feed forwards, not the traditional type of feed forwards, but what I call a command or target feed forward. The reason why I have two different terms for it is because I probably worked on this project about 5 years apart and I couldn't remember what I called it before. So I've used both the words target feed forward and command feed forward. The traditional feed forward works like this. You have a target position. And what you do is you differentiate that, you get a target velocity, then you differentiate that, you get a target acceleration, and then a target jerk, and you have a different gain, and you add that to the output from the closed loop part. So this is open loop, and this is closed loop. And this works fine as long as all the gains are in the forward path. That means all these gains are working on the error. So sometimes it is feasible to have the integrator work on the error only, and then the proportional gain and the derivative gain and second derivative gain act on changes in the actual position. And what that does is it slows down the response, but it also makes it so you don't get overshoots due to having zeros in the wrong spot. So this is the traditional way of doing feed forwards. It's what they use in most motion controllers. But I'm going to show you a different way of doing it. Let's see. Let's go back up. Oh, let's close this. Okay, here we go. So what we want to do is use a proportional only because it doesn't have any zeros that will extend uh, the bandwidth. So if we just use a proportional gain, we're going to get a response that looks like this. And if we use a proportional gain with a target feed forward, then we can get a response. You can see there's a lag between target and actual. And here the target and actual are right on top of each other. And the way that I did that is by having what I call a target or command feed forward, which is this black line. And this is kind of analogous to having holding a carrot out in front of a donkey. And what you're doing is you hold the carrot out where you want the donkey to go. And sometimes you have to exaggerate the path a little bit to get the donkey to go exactly where you want to go. So by having the closed loop part act on the error between this target and the actual position, you can actually get the uh, target and the actual to line up, the real target, which is this cyan line underneath here. And then we can look down below here, we can see the target and actual velocity. And basically what I did here is I just copied from one to the other and changed the title. So you can see that there's a lot of phase lag in the velocity, and there's a lot of phase lag in the acceleration. And to generate this motion profile, what I did is I told the simulator to move to 400, from 0 to 400 millimeters, and to do it in 1 second. And you can see that because the phase lag, it takes a little bit longer than 1 second to get into position. Whereas here, it happens in exactly 1 second. So using this target feed forward uh, speeds up your process, and I'll show you a place where it really speeds up the process. But first, let's go take a look at how this is achieved. The top part here is my traditional closed loop calculations where I have the proportional gain for the controller, and this is my plant, which is a linearized hydraulic system. And I'm assuming that the valve is responding pretty quickly, so I don't have the valve in here. This is the open loop gain, the natural frequency, and the damping factor. This is the definition of a closed loop transfer function. So I do the substitutions, and I get this equation. And if I simplify this, my closed loop function is a denominator which has no zeros and a numerator that has no zeros and a denominator that has 3 poles. And what we want to do is place these 3 poles with this one gain, and it's impossible to do because you need 3 gains to place the 3 poles, but I can at least put the 3 poles in a uh, optimal place. So this is my desired closed loop transfer function. I have one pole that I'm going to place at minus alpha, and I have the two imaginary poles that are going to have the real part at minus alpha and the imaginary part plus or minus beta. So this is the, when I expand that out, this is what the desired closed loop transfer function is going to be. Then this is my shorthand way of calculating out the gains. Basically, again, what you do is you just match the coefficients and solve. And what happens is I get a Kp, which is equal to this term here, a alpha, which is this term, and a beta, which is this term. So this is going to be plus and minus. That's why there's two rows, because there's a plus and minus complex imaginary part for the poles, or for the poles. So let's assign some values. The one on the right is identical, so I'm just showing you the one on the left. Okay, so the optimal closed loop gain for the proportional gain is 1.2. And I see I've assigned a natural frequency and a open loop gain for the controller. And for those people that are hydraulics oriented, use the VCCM equation to find what the open loop gain is going to be. This part is calculating out what the state space arrays need to be. I'm not going to go over this in too much detail because I've done that in many of the other videos. But basically, this is the the continuous state alpha A array and the B array. And this is the input coupling. This is the transition matrix. And then I have to convert that to a digital format, which is done down here. This is the equivalent of an EXPM equation in MATLAB, but MathCAD does not have EXPM equations, so I have to do it the hard way, which is what you see right here. And then I have my simple PID, which is really just a proportional only. So this updates the state, and this is the control output, which is Kp times the error, and I'll limit that to plus and minus 100%. Then I have, in this case, my first simulation here is doing a step jump. And notice that it takes, to go 20 millimeters, it takes about 0.3 seconds. And it doesn't make any difference whether I'm going 10 millimeters or 20 millimeters, because it just, it takes 0.3 seconds. Because the when you do the Laplace transfer, the inverse Laplace transform, all the errors decay as a function of e to the minus alpha t. So no matter how far you want to go, the errors are going to decay at the same rate. So here I'm moving 1 second and 400 millimeters, and I'm calculating out the maximum velocity, average velocity, the time. And this is my fifth order target generator, and this is doing the PID again, and that's how I arrive here. And the right side over here is the same, except for I calculate out what this target feed forward needs to be. And this is the magic. So this is the closed loop transfer function from above. Let me just go back up here. That's this part right here. And what I want to do is take the inverse of that and find the coefficient. So I get a 1, and this is my target position coefficient. And then I got a velocity, target velocity coefficient and acceleration and a jerk coefficient. And this assumes that you have a motion generator that will generate a smooth position, velocity, acceleration, and jerk. And basically, my target feed forward is this matrix right here, which has these values. Oops, didn't want to do that. So when I multiply the target feed forward times the target position, and that's what's different between, let's go down here again. You see right here, I have, this is my target position generated by the fifth order target generator. And this is the current state. And you can see the difference here is I just have to multiply this matrix here by the target. And then what it does is it makes this leading command target right here for uh, the error. So what happens is that this difference between here and here is compensates for the phase lag from here to here. Very simple. Now, where this really makes a difference is on short moves, because on a short move, let's just come down here. I got a short move. Oh, I got the Bodie plot. I'm not going to spend too much time with this. You see, this is my closed loop transfer function. So that's a closed loop Bodie plot. And the zeros. I want to show you this, though. You see, I've got 3 poles, and there's no zeros. And this is the one real pole that we place with the S plus alpha. And then these are the 2 imaginary poles. And the problem with this closed loop transfer function is that if I want to move this pole closer, these poles move away. Or if I move this one this way, these 2 poles will move here. And that's definitely not desirable, because then what happens is you can see oscillations. But if I move this real pole closer, it slows down the response. So this is really about the optimal placement for the 3 poles. But I only have 1 gain, so I can't place these 2 extra poles at the same location. Another thing I want to point out for the hydraulic people, let's go back up here, is that this is the formula for alpha, and you can see it's dependent upon the damping factor and the natural frequency. In other words, the response to the system is dependent upon the mechanical features of the cylinder and the damping factor, and the poor control guy can't do anything to really speed it up from there, except for to use these feed forward tricks. So now let's talk about the feed forwards again. So, okay, we to recap here a little bit, we take the inverse of the transfer function, we get the transfer feed forward, then we just need to multiply that by the target, and we get this command, this kind of like moving the carrot out in front of the donkey, or exaggerating the position. So the actual falls right on the target, your real target. And this is where it makes a difference. In this case, what I'm doing is I'm making a short move, and I'm only moving 10 millimeters. And the problem with the system without the feed forwards is that it takes about 0.3 seconds to move the 10 millimeters. And like I said, it takes about 0.3 seconds to move 10 millimeters, 5 millimeters, or 20 millimeters. But here I'm using this command feed forward, and you can see it's widely exaggerated here, but I can get from 0 to 10 millimeters in 0.1 seconds. That's what I have set up down here. And so I can get much faster motion. So basically what's happening is that the actual position is trying to follow this target here, but because of the phase lag, it's actually following exactly on our real target position, which is down here, and we can make the motion in the desired amount of time. So that's the big advantage. And then down here, this is without the target feed forwards. You can see that it takes about 0.3 seconds, maybe even 0.4 seconds to move 10 millimeters. So the thing I want to point out is that there are 2 ways of doing this feed forward, and the target feed forward method has the advantage in that it can work with systems that don't have any zeros, whereas the traditional feed forward requires that you have all your zeros. All the gains act on the error between the target and actual values. With the target feed forward method, you don't need to have any zeros, and you can get pretty much the same result. So that's it for this video. And if you have any questions, just post them down below. Bye.